So everybody's got their calculators. Several things that I like about these TI-30XS, especially for use in our classrooms. One thing I really like is that they're solar powered, so batteries shouldn't be a problem. I really like that they're multi-line in their display. You've got parentheses, you can do grouping, you can really see everything you've entered. You have a small number of variables that you can store things in if you need to keep numbers on hand for reuse, but they don't have extensive memory, and they don't do a lot of things that we don't really want to do in our calculators anyway, like matrix manipulation and graphing equations. But all of our basic operations are here. So in fact, what we want to do over the next few days is work our way through the rest of these kind of basic operations. So we've spent a little bit of time doing our kinematic equations, and the function of our kinematic equations, basically speaking, was not only to give us a little glimpse of some basic physics applications, but also to be sort of a test bed to practice solving simultaneous equations and making substitutions, making sure that we can undo all of the operations in the reverse order in order to isolate the variable that we're interested in. Last time, of course, we met the quadratic formula. In the notes that I've given you, if you'll read through those notes carefully, there's actually a graphical proof of the quadratic formula, which I'd like for you to work through. We probably won't do that in detail in class, but in the notes that I gave you, there's graphical proof of the quadratic formula. And as we pointed out last time, the notion of the quadratic formula is that any of those functions whose highest power is a square are going to take the form of a parabola. And we always expect that our parabolas will have two roots. In other words, two solutions for y equals 0 where they cross the horizontal x-axis. Of course, that can break down a little bit. If we have a situation like this or a situation like that, as we discussed, this curve seems to hit the line only once, and this one seems to not hit the line at all. And as one of you pointed out insightfully last time and correctly, this is the sort of situation, for example, where we didn't shoot our arrow fast enough to ever make it up to the tree branch. So we never had a solution that physically came out. The manifestation of those unphysical solutions, the way that the math kind of screams at you to let you know that something unphysical has happened, is that that quantity underneath the radical goes negative. And taking the square root of that negative number is no longer a real quantity. Now, as you all know, we can make a definition that the square root of -1 is this new symbol that we're going to call I. And we'll find as we progress through the semester that this is really an incredibly kind of powerful thing to do. It may be that when you first encountered these imaginary numbers in high school, let's say for the first time, and you said, okay, I can work with these things, I see them, I know that when I square them I get a negative. But it may not have been obvious why they were useful. It turns out they are not only mildly useful, they're radically useful. They're incredibly useful. You can get almost nowhere without them. And the first thing, I think, that's most intuitive to grasping what's important about these things is that they let us keep this notion that we always have two roots to a quadratic equation. There are none on the real axis here, but nevertheless, the fact that this curve doesn't ever intersect that axis will imply that under the square root sign associated with the looking for its roots, we have a negative number, and therefore that the roots are imaginary. And as we transition between intersecting twice and not intersecting at all, there are intermediate cases between those that intersect just once. And that's where the thing underneath the radical goes exactly to 0, so it's plus or minus 0. And we can still, in essence, claim that we have two roots. It's just that both of them are repeats. Degenerate is the word that we use, a bit of a vocabulary word in that case. Degenerate in this context means repeated. It means not unique. The thing happens multiple times. We can kind of generalize this notion that whenever we have cubic equations where the highest order of the polynomial is 3, in general we should have 3 roots. So the most simple cubic that we can draw is something like this. Y of x is equal to x cubed. If we think a little bit about how that behaves, over on this side it's going to look pretty much like our quadratic did, except it's going to be growing even more steeply as we get larger than 1. We have 1, 1 there. 1 cubed is still going to be 1. There's something interesting there. I can blow that up a little bit so we can see it better. 1, 1 there. Just sort of a dotted line across there. For example, when we graphed x squared, or now when we're graphing x cubed, they kind of go like that, right? That's a very important thing. It's an important thing to notice that has lots of interesting ramifications all over the place. If you take a number which is less than 1 and you square it or cube it, it gets smaller. See how those are on the underside of that y equals x line? On the other hand, if you take a number that's bigger than 1, if you square it or cube it or fourth it or eighth it, it gets even bigger. That's an important property. It's related to the idea that whenever we say that something is small or large, this is an idea that's going to resurface several times over the course and through the semester. We'll have several examples of it. Whenever we say that something is small or large, we always mean that how? Relative to something else. To say that something is small or large only makes sense if you're comparing that thing to something else. And there's one exception to that statement, which basically means that you've already done the comparison. The exception is that you have a quantity with no dimensions in it, just a number. If we're talking about just pure numbers, big, we mean bigger or generally much bigger than 1. And they have the property that when you square them or cube them or fourth them, they get even bigger. And small, we mean much smaller. So let me give you some examples. One very relevant example would be speed of light. Right? Nature gives us a fixed speed of light. The fact that we have a fixed speed of light is not trivial or obvious. It's a profound experimental fact that the fastest speed exists in nature. Nothing can go faster than that. It's a profound experimental fact. So when we do, for example, particle physics analysis, and we're interested in things that are traveling really, really fast at relativistic velocities, usually we express those velocities not in meters per second or miles per hour or anything that's just based on human-sized units, right? We express it in terms of units that nature gives us. In other words, nature tells us what the maximum speed is, minimum speed is 0. Where are you on that number? So we actually measure our speeds with no units at all because we're measuring them relative to a fixed speed that nature gave us. So speed 1 is the maximum speed and it has no units on it because we're already doing a relative comparison. And then anything less than 1, less than the speed of light, becomes a smaller and smaller and smaller ratio. So to finish graphing that curve, the y equals x cubed on this side, it goes up like that. So it's below the y equals x line until you get out to 1, and then afterwards it's going steeper and steeper and steeper, and farther above the y equals x line. Same magnitude as we go to negative, but it has a different property than the square, which is that the cube of a negative number is what? Negative. It's also negative. So 3 negative signs. Negative times negative gets you back to positive, but then one more negative stays negative. So on the left-hand side, this thing goes like that. By the way, also an important bit of vocabulary. This is what we call an example of an odd function. An odd function means that if you flip the left for the right, that's the same as flipping the top for the bottom. Another way to say that would be to say that y of negative x is equal to negative y of x. Does the equation make sense to everybody? So, for example, in other words, y of 5 and y of negative 5 are exactly negatives of each other. Not without cause, the odd functions also correspond to odd numbered powers, an uncanceled number of negatives. And conversely, the function that we were looking at previously, the quadratic function, the square power, even function, y equals x squared, and it has that symmetry. Y negative x is equal to plus y of x. And correspondingly, for example, even powers, even numbers as the power. Make good sense to everybody? What we're going to proceed with today is a look, as I was describing, into a few other and slowly more exotic types of functions. There's several types of functions that we run into that are most important in our analysis. And basically speaking, they're the functions that appear on your calculator. We need to be able to raise numbers to powers. We need to be able to undo any operation that we can do. We need to exponentiate and be able to take logarithms. The distinction between those two ideas, as we'll clarify increasingly over the next couple of days here, is whether you think about the variable you're interested in being the base or the exponent itself. There's a little bit of a distinction between those 2 points of view. So what we want to start off with today is just kind of going back to scratch and thinking very primitively, very simply actually, about the way that some power rules work, and along the way, hopefully, get a little bit of insight that maybe was kind of lying there in front of us all the time, but we hadn't maybe ever noticed it. And we want to understand why some of the rules that we're familiar with work the way that they work. So for example, if I write something like this, I think everyone knows what that means. That means take whatever A is and multiply it by itself 5 times. The A times A times A. Simple enough. Now, what is a little less obvious until we inspect a little bit further is the way that things behave when we have multiple bases raised to different powers. We want to combine those things together. If we just think about that a little bit, it'll be real clear to us what the rule is. And once we understand the rule and generalize it a little bit, there will be maybe even surprising consequences that we hadn't realized before. Ways to understand things that otherwise would seem a little bit mysterious. If we do something like A3 times A squared, well, we know what A3 is and we know what A squared is, right? So A3 would be A times A squared would be A times A. And with just a little bit of thinking, we can convince ourselves that the rule for this ought to be that that's the same as that. So if we have common bases and we multiply the thing 3 times and then multiply by itself 2 times, for example, it's the same as multiplying by yourself 5 times. So the rule pretty generally there is A to some power n times A to some other power m is just A to the n plus n. Are you happy with that? Now, if that's the case, we immediately begin to understand some other things. One of the things that we can understand, if that rule continues to hold, is what it means for a power to be negative. So what if we wrote something like that? Is it obvious immediately to us what that means? And I think probably most of you know what that means, and you've seen it, and you've learned this rule at some point. But I want to strip back to kind of elementary considerations and just kind of think these things through from the ground floor, right? And really get a firm idea of why it is that these things are the way that they are. What does a negative power, for example, mean? So for example, if we had A3 times A negative 2, if we follow our general rule, that should be the same as A to the what power? 3 minus 2. Which should be the same as A to the 1, which is just A. Now, if we expand each of these things out, A cubed is A times A times A. And the question is then, what is this thing? What is the A negative 2? Such that when you multiply it with A times A times A, you get just 1A. The answer's got to be that A to the negative 2 is like, since it's canceling out those powers, it's got to be combined. So the conclusion that we come to that's very important in this is that A to the negative power is 1 over A to that power. And we can reason that this ought to be the correct rule just by extending that pattern that works correctly for the positive numbers into the negative numbers. Another one here that's interesting. It can be a little mystifying the first time you run into it. A to the n times A to the minus n. Well, that's got to be A to the n minus n, right? In other words, it's got to be this base raised to the 0 power. But if we know what each of these things are, it's going to be A to the n divided by A to the n. In other words, it's got to be 1. So we learned something very interesting that also follows just out of these very basic considerations. And it can seem mysterious. At some point someone tells you, but for consistency's sake, this is the way we've got to treat that thing. If we raise something to the 0th power, it's always got to be 1. Very, very important. Another set of things Another set of operations that we could be interested in is something like this. What if I took a quantity and cubed it? Be a little careful with where the parentheses are here. If I take that quantity and cube it, and then I square it, let's think carefully about what that means. So A cubed I know how to deal with, no problem there. That's A times A times A. But now that thing's got to be squared, right? So if I square that thing, that means just take all of this and multiply it all by itself one more time. So that's got to be A times, if I got times A. In other words, how many of them altogether? 6. Okay. So did we start to see another rule popping out?
Yep.
Yeah. We raise something to a power, and then raise that whole thing to the power again. Now, careful. This is, it's not the same. It's not the same as that, right? That would be A to the 9th. That's a completely different thing, right? Because 3 squared is 9. So we're not applying the square to the power. We're applying the square to the quantity. There's the distinction between those two. But it seems to be then, if we raise A to some power n, and then raise that whole thing to some power m, the rule's got to be that this is the same as a to the what?
N times
A to the n. Okay, pretty neat. Good so far? Everybody tracking? You've seen all these things before, so but let's make sure we know where they come from. We want to really feel them in our bones. This has wild implications again as well. This has wild implications again. We know what raising a thing to an integer power is. We know what raising a thing to a negative power is. That means divide by the thing. What about raising a thing to a fractional power? Now, you notice something here. For example, if I take a to the fifth, okay, and then I raise that whole thing to the 1/5, that's got to be a to the 5/5. So a to the 1, which is just a. So what that means to us is, again, something interesting, which is that these fractional powers are actually doing what? They're taking, not dividing. It's more subtle than dividing. It's an inverse of raising to the power. What's the inverse of raising to a power called? Not necessarily a square root, but yeah, taking a root. In this case, it wouldn't be the square root, it would be the
fifth root.
It would be the fifth root, exactly right, but taking a root. So we learned something interesting. We learned that if we raise a thing to 1 over a power, that's the same thing as taking the nth root of that thing. So this is our rule, most commonly that you see, which is that raising a thing to a 1/2 power is the same as taking a square root. Raising a thing to a 1/3 power is the same as taking a cube root. So those are very important rules. Now, one thing here to be a little careful of, there's a subtlety here that I've really glossed over, and you have to be a little bit careful. In particular, with this rule, a little bit of caution is in order. Be a little careful with that rule. The reason you need to be careful with that is that it can be multi-valued. And in particular, some of the roots can be negative. As we've seen explicitly, if we take a square root, how many do we always get? 2. If I said negative, I meant complex. In particular, the roots can be complex. So 2 roots, always if we take a square root, it's always the plus or minus the radical. But if that discriminant, the quantity under the radical, goes negative, then our 2 roots are, in fact, complex conjugates of each other. They're imaginary numbers, or complex numbers. In general, if this were a 5th root, there would be 5 answers. And we'll prove that a little bit farther along. We'll need to understand complex numbers a little bit better before we can prove that and really understand what the reason for it is. But I think even early on, you can see the intuition. We drew that graph when we drew y equals x cubed. It was like that. And I can tell you it has 3 roots, but you only see 1, right? Because they're all stacked on top of each other. But if you turn the coefficient in front of the square and turn the coefficient in front of the linear and turn the constant coefficient a little bit, you can distort that shape a little bit. What you can do with that shape, is ultimately distort it, for example, so that it looks something like that. It becomes real obvious in that case that you have the 3 roots, right? If you go to a 4th power, along with some squares, you can have a graph, for example, that looks like that. And it has 4 intersections. This graph, by the way, is really, really important in physics. This is related to what's called Higgs particle, or the Higgs boson. Have you heard about the Higgs? This is the particle that gives other particles in its interactions masses. It was discovered in 2012, just a few years back, at the Big Particle Collider in Switzerland. And this graph, which we'll spend a little more time with this semester as we get further along and play with, because it's a really neat graph, actually is telling us the story of the Higgs in some sense. I want to give you an idea of what a function like this might actually look like. So for example, this could be y equals negative x squared plus x to the fourth. That would be an example of a fourth order polynomial line. While we're on this, I'm going to spend just half a second giving you some notion of how you could know that that was the graph of that function without having to plot it on some calculator, without having to think about it very long. Here's the idea. In fact, it's an idea we already talked about today. If you take a number that's bigger than 1 and you square it, or you fourth it, or you ninth it, it gets even bigger. If you take a number that's less than 1 and you square it, or you 16th it, it gets even smaller. Okay? But the question is, which power is going to dominate in certain regimes? Which power is going to dominate in certain regimes? So if I have a number that's very small, x, what I mean by very small is very close to the 0 point of my x equals 0 line. If I have a number that's very small, if I square it, it's going to get smaller, right? But if I fourth it, it's going to get even smaller. Or if I 12th it, it's going to get really, really small. Does that make sense to everybody? So in other words, when I'm close to x equals 0, who's going to win? Who's going to be the dominant term? The square or the fourth? The square. Makes sense. But for numbers that are much bigger than 1, bigger numbers, which is going to give me a bigger outcome? Just squaring it or fourthing it? Fourthing it. So what do I learn? I learned something very important. This one wins for small values of x. This one wins for large values of x. This one had a positive coefficient. This one had a negative coefficient. So in here close to x, when I'm real close to x, it just looks like negative x squared. But ultimately, at the end of the day, this guy's going to win. And since it's an even power, it's always positive. So this thing's ultimately going to go up like that as I get far away. The way that this quantity becomes important in particle physics is because it's got a minimum of that potential energy function. Systems always like to oscillate around the minimum of their potential energy function. It's a story that we'll come back to several times this semester. Systems always like to oscillate around the minimum of their potential energy function. This is a local maximum. For example, if you thought about a skateboarder, standing on the top of that hill, is that a safe place to stand when you skateboard? Because just the tiniest little push is going to send you off that way. So this system, actually, as the temperature of the universe changes, this coefficient, in some sense, goes from positive to negative. And if both coefficients are positive, it just looks like that. So the minimum of the potential energy is at 0. But if this coefficient ultimately goes negative, that system turns over. And where does the system want to be? Not here, but at one of these minima. Actually, to be even a little bit more truthful, it's a complex number function, and there's a whole ring of minima that we might go down. And the universe, in some sense, falls into one of those. Which one? Well, whichever one. It's called a spontaneous, because it just falls into one of those processes. It's called a spontaneous symmetry breaking. And it's responsible for giving all the particles you're made out of mass. It's a big story. I'll talk a little bit more about it as time goes. But it's just an example of where these polynomial functions are useful. And we've now generalized this idea a little bit more to these sets of rules, which will be useful to us all semester long. Again, with the caveat there that you have to be a little bit careful of this. If you take a fourth root, there will be 4 of them, so you may not have gotten the one that you meant to, unless you really consider all 4 of them. And that will become more clear once we really start talking more seriously about complex numbers. So here are our rules for the way that powers behave. So all of those should be known very clearly to you. I mean, in some sense you can memorize them, but at a different level, you've got to know them. You've got to really feel these in your bones. They've got to be very, very clear to you. So I would suggest, going back through those notes a few times, do the simple cases, test them yourself, make sure that these rules make sense to you. So when you use them over and over and over, and feel lots of things out. Now, the next thing that I want to talk about for a while here, to kind of close out this section of our basic functions and actually get us most of the way there, other than our trigonometric functions, which we want to spend some time talking about, is to talk about logs and exponents. So the distinction in some sense relative to the power series here, we're thinking about power series, it's sort of just a point of view issue. We're still raising things to powers, but this application, generally speaking, we think of the power as a constant and the base as a variable. It's almost just sort of a point of view exchange. Of course, if you're graphing, your horizontal axis becomes the variable. It's very important which of those quantities you consider to be the variables. So they are distinct, but it's kind of a point of view issue. When we start thinking about logs and exponents, the thing that's going to be different and the thing that's going to be important is that the variable is upstairs. The variable itself is up in the exponent. So, for example, you can have f of x is 10 to the x. So what we've done explicitly in this example is we've made the base be some constant number, and 10 is a very common base to use. We happen to have 10 fingers, right? If we had ended up like that, we could all use base 8 count. 10 is very handy. Yeah. And then we can raise that 10 to different powers. These exponential functions grow much, much faster than the polynomial functions. They really shoot up. And the reason is because changing that in some sense is more effective than changing that. As we work our way out on the axis, we're getting to bigger and bigger and bigger powers. So for example, if I had drawn that function, f of x or y of x, whatever you want to call it, function which depends on x. Of course, again, when we see those parentheses, we pronounce it as of. But be careful though, sometimes when we put parentheses, we mean multiply, so it's just be a little sensitive to context. So f of x, some function which depends on x, call it y. Y of x is 10 to the x. Now, we're going to have a real hard time graphing this, as it turns out, because the thing's going to get big really, really quick. Now let's put in some values that at least we know the answers of, okay? 1. Okay, good. X equals 1. 10 to the 1 is what?
10.
Perfect. So if this is 1, what, I better slice that up a little bit. I didn't get anything on the graph at all. Okay. So f of 1, this is x, this is y of x. Oh, I guess there's our y, isn't it? F of 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There it is. What's another one that's easy?
0.
F of 0. 10 to the 0 is what?
1.
1. All of our exponential curves pass through that y of 0 equals 1, unless they have a coefficient out in front that gives them a scale. What about negative 1?
110.
There you go. Yeah. So negative 1, 10 to the negative 1 is 1 over 10. 1 over 10 to the 1. So that would be a 10. Now, what about 2? 100. Oop, I'm out of room. Over here, at least I can try. F of negative 2 is 100, and then 1,000, and then a 10,000, and then a 100,000. So, oh, I missed it. Steep. These are very, very steeply behaving functions.
It's just gone.
What's that?
It's just gone.
It's just gone. 10 is a very common base. What are other common bases? 2 is a very common base. What's special about 2?
It's easy to figure out.
Yeah, I would say it's the minimal non-trivial case, I guess, integer anyway. It's also the system on which all of our computers are based. So binary. So if you want to store information, for example, in a byte of data, everyone knows what a byte of data is. How many bits? 8. So in a byte of data, you've got 8 bits, and each of those bits is a digital register, which can take 2 values, right? Usually you call those 2 values what? 0 or 1, exactly. So let me ask you this. If I had one digital register, 1 bit, how many values can I hold? How many different possibilities are there for that 1 bit? 2. If I've got 2 bits, how many combinations can I make? Yeah, that's right. 4. Everyone see that? Because I can do. Here I can do 0 or 1. Here I can do 0, 0, or 0, 1, or 1, 0, or if I have 3, I don't want to write them all out. How many? Careful.
6.
No.
Not 7.
No.
8.
Everyone think about it for a second.
It's not.
It's not 9. Oh, that's the wrong pattern.
3.
Maybe 12.
No. Everyone think about
3
it.
to the third.
Not 3 to the 3rd.
2 to the
2 to the 3rd. 8. 8. Okay. Think about it this way. Because I had 4 possibilities there, right? For my first 2 bits. And then I can do each of those 4 2 different ways with my 3rd bit, right? So this would be 8. If I had 4 bits, how many combinations? 16. Yeah. So what's the pattern here? It's 2 to the n. There we go. 2 to the n. So a byte of information is how many bits? 8. How many possible combinations can I make with 8 bits? 2 to the 8. What's that number?
256.
Have you ever heard that number, 256? So 256 combinations. This was at the heart of what they used to call, well, still call, the ASCII designation of characters. So within ASCII, so for example, all the things that you might type on a keyboard, right? Like lowercase a, capital Z, and all the things in between, and your numbers, and your apostrophes, and your commas, and your different types of brackets, right? All of those had a number. there's less than 256 of those things. They all had a number, and they could all be recognized as a character within the 8-bit thing. Have you ever opened up like a Microsoft Word file, but in a text editor, something like that, and you see lots of garbage, right? Some of those characters are not within the range of the 256 values, the things that you're normally used to. Of course, people discovered that not everyone speaks English, and that the Western keyboards aren't good for everybody, and that we might like other types of symbols to incorporate various cultures, to make little emojis out of, for example, little smiley face signs. So these days, there's a higher set of designations. I think it's called UTF-8 or something like that, which extends off beyond ASCII. But the point is that it's based on this exponential type counting, which underlies all of our computer-based manipulation. By the way, before we leave that, I want to take just a little second to show you how to count in binary. Okay. This is a neat thing. A thing worth knowing. A very nice example of these exponential functions. So we have numbers starting from 0, our counting numbers, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, I want to represent these as binary digits, combinations of 0 and 1. Now, how many numbers have I got listed there? 11 is the right answer. So how many bits am I going to have to use to make sure that I can at least get all of those on the screen? 4, that's right. Because 2 to the 3 would be 8. That's not enough, right? 2 to the 4 is 16, so I'm going to have a little, I'll not be out before I reach 10. Well, let's write this in 4-bit notation then. What do you think 0 is? Can you guess?
0.
What do you think 1 is?
1, 2, 3.
That's a good guess. There's actually, you have hit on an interesting controversy. Do you guys remember the story of Gulliver and Lilliput and Gulliver's Travels? Have you ever heard the story? And there was the big people and the small people, and there were the people who opened their eggs from the small side of the egg, and from the big Indians and the little Indians. A major similar war was waged over how binary numbers should be represented, with the least significant bit on the left. Actually, it's not like that. Can you guess what 2 would look like?
0, 0, 1, 0.
That's right. Now, can you guess what 3 would look like?
1, 1.
That's right. You see kind of the odometer clicking. You see how this is working. What's going to happen next?
0, 1.
That's right. Then 0, 1.
0, 1.
Yeah. Then 0, 1. 1, 0. And 0.
1, 1.
And then finally.
1, 1.
Oh, good. Now, you guys did perfectly on that. Before we break, let me clarify for you what the pattern was. So this was the 0 column, the 1 column, the 2 column, the 3 column. Yeah, in terms of what power we're looking at. Okay? So as you read across, any of the ones that are 1s, you take 2 to that power and add it together. Yeah, so very clever. So 8 here is 2 to the 3 and nothing else, that's 8. 6 is 2 squared, which is 4, plus 2 to the 1, which is 2, and that's 6. And you can build any number you like out of this. And then you can think about how to add these things on a computer using silicon, which functions as little gates. You send inputs in, certain different inputs out. And you can use electrical signals, high voltage, low voltage, 0, 1. And you can use these to add numbers together. When we get back on Monday for the weekend, let me ask you to read through that batch of notes that I read. I'm going to give you some new notes on Monday. And when we get back on Monday, we'll kind of do what we did for the powers and build out several of the rules that we need to be real clear about. Again, from ground rock, first principles, just what's the first thing that makes sense, and can we build up on top of that for the logarithms and exponents for and how to change bases. We'll be real sure 100% everyone knows what a logarithm is. And I'll see you back then.